Okay, welcome everybody. Today we have Sujit Sarkar, and he will talk about topological quantum criticality in non-Hermitian extended Kitaev chain. So, Sujit, when you're ready, go ahead.
Yeah, okay. At first, I would like to give my deep gratitude to the organizer of the PhD, especially Professor, and he has given me the invitation for this, and also I feel proud to present this seminar, online seminar in this international platform. And the title of my talk is discussed the topological quantum criticality in the non-Hermitian extended Kitaev chain. And also the thing is this, this is my affiliation, and the acknowledgement is the Roman Research Library. A major part of my research work I spent in this library, and also this PhD seminar series from where I learned many aspects, and also the many good references I got it. Okay, and also my PhD student, Ahul, has submitted the thesis, has already been, and he is a postdoc in the IIT Chennai, India, southern part of the India. And these are my PhD students, Ahul, Artik, and Ranjit, and Ilanjan is one of the collaborators who is collaborating with us. All of them are quite intelligent and efficient with me. I'm lucky that I got my student and also the collaborator like Ilanjan. The outline of the talk is the introduction, and then I will introduce the non-Hermitian ordinal Hamiltonian, followed by the results and the conclusion. In the introduction, I will present what is the parity times symmetry and its importance, and the Hermitian counterpart of this non-Hermitian ordinal Hamiltonian and its result. Actually, I would like to say the whole thing. That is this Hermitian physics. I would like to explain at length in the introduction, and then my main motivation, if I change this ordinal Hamiltonian to this non-Hermitian one, okay, by changing the chemical potential term, how the all physics will be changes for the Hermitian Hamiltonian, okay. And actually the topological quantum criticality, that is the main thing that we wanted to study. The references of this work is this. At first, the Hermitian ordinal Hamiltonians and introduced by the A. Kopp and Sujit Sarkar in the HR Physics, first volume, 2005. It is one of the weakest cited work in the whole literature on the not only for the quantum criticality but also for the topological state of matter. Me and Rahul has done this work. Actually, I have started to work on the non-Hermitian quantum physics, quantum anybody or quantum field theory in the first lockdown when I was with my mother in the April 2020. And when we started this work, 4 or 5 works we have done in this field, and all of them are highly appreciated across the scientific community. And this is the case. Today, mainly I present this result, topological quantum criticality in the non-Hermitian extended Kitaev chain. It has appeared in the Nature Scientific report, and this is the references, and also the other references by the Professor Ender, PT symmetry in quantum and classical physics. I have learned also quite a few things from this book. I have a personal copy of this book, and apart from this, in this work, I would like to present her. I would like to present something on the ordinal Hamiltonian, the Hermitian part. What is the Hermitian Marana Euro mode and the bulk boundary correspondence at the criticality, and also the a part is the multi-critical topological Hermitian point. Also, it has appeared in the Nature Scientific report in the last year, and also this at first the new et al. At first the Professor Sujit Sarkar has introduced this ordinal Hamiltonian in the Nature Physics journal, but after this, he has published one very good paper in the PRB to 2085 to 2012 at around 200 citation across the world. Mostly the people see of this model Hamiltonian in terms of the topological state for the Hermitian system. We take the challenge how to change and modify this Hermitian model Hamiltonian to the non-Hermitian one, and how the topological quantum criticality bulk boundary correspondence with the change. And also this other one that I wanted to go ahead. So very basic introduction is there. Today I saw Professor Carl Bender in this audience. I'm so happy that I'm presenting my online seminar. Professor Carl Bender is one of the audience of this online seminar. So the thing is this, I have taken this from internet source from Professor Carl Bender and other. The summary of the possible one very briefly. Okay, the thing is this, the Hermitian operator, we know the from the fundamental theory closed system, it has a real eigenvalues. Okay, and now the question is this. Okay, the non-Hermitian operator with the isospectral transformation and the unbroken symmetry, the system has a real eigenvalues. Okay, but the broken symmetry will guess for the non-Hermitian operator, then this complex eigenvalue, we are getting the complex eigenvalue. Okay, and this is the article, a popular article from the Professor Bender. I have taken it from the internet source, but now I forget the actual references of this article. It is symmetry in quantum physics from a mathematical heuristicity to the optical experiment. Okay, the thing is this, the when Professor Bender is one of, and his consequences in the many consequences in the mathematical physics. So his when we start his ERL paper, Bender and Bocher in 1998, whether he solved the very rigorously this problem by introducing a non-Hermitian cubic term in the Schrodinger model Hamiltonian, the space-time reflection symmetry or the PT symmetry, first proposed in the quantum mechanics by him, has become an active research area in the fundamental physics. More than 2,000 papers have been published on this subject, and the papers have appeared in the 2 dozens of the archive of over 2 dozen international conferences and the symposia, and especially devoted to the PT symmetry has been held, and many PhD theses have been written. Today, I am going to present mainly the chapter 5 of the PhD thesis of one of my PhD student, Rahul S. Rahul has submitted this thesis, and mostly he will get the degree in the next month or so. Okay, he is a postdoc in IIT Chennai, India, southern part of the India. The title of his thesis is the studies on the state for Hermitian and the non-Hermitian topological system. The thesis is submitted under my supervision. So quite a few important aspects of the non-Hermitian quantum physics. I am not using the all, but a few. The excitation spectrum is no longer the real, the physics of exceptional point and the modified bulk boundary correspondence. Sorry, there is some mistake. Okay, the spelling mistake. The topological aspect of the non-Hermitian system is far more enriched than the Hermitian counterpart, and the physics of quantum criticality for the non-Hermitian system is far more enriched than the Hermitian counterpart. The model Hamiltonian is I can explain this as far as the Hermitian model Hamiltonian. It will explain us to the basic physics. In the last 2 years or more than that, I am attending almost all conferences, this seminar. So this model Hamiltonian, I never saw any of the speaker exposed. This is the model Hamiltonian. You can see this model Hamiltonian is the 3 parts. the part 1 and the part 2, part 3, the first part and the third term is nothing but the quantumizing model on the transversalizing model. People know 1950 onwards of this, 1972 onwards of this model Hamiltonian, this first term and the third term, but the second term is this, that is the addition for the longer range interaction. Okay, in this longer range interaction, you will find this term. Okay, and now the question is this longer range interaction. If you see the only the quantumizing model lambda 1 and the mu term, in the quantumizing model you can find the competition with the lambda 1 u. The system is either in the ferromagnetic phase or in the quantum spin liquid state, or in other words in the quantum disorder paramagnetic phase. But the lambda 2 term is the three sides term, that is the I minus 1, I and I plus 1, I minus 1 and I plus 1 if the ferromagnetic interaction, but the I and I minus 1 give the exact interaction, and the I and I plus 1 will give the exact interaction. So this term will give more enhancement of the quantum disorder state, topology quantum paramagnetic state. So there is a now competition between the lambda 2 and u term also, and also the lambda 1 and u term, also the lambda 1, lambda 2 term. But the thing is this, in this case, we have not exposed in that way. This is this quantum phase diagram. Ether, we are very much using the topological state of ether. If we do the Jordan-Wigner transformation, through the Jordan-Wigner transformation, I can recast my the spinless Fermat to the spin Hamiltonian to the spinless Fermat Hamiltonian. I have write down in terms of the Jordan-Wigner transformation, and then if we go to this equation number 2 to the reciprocal space after the Fourier transform to the momentum space, I can write my Hamiltonian in terms of the Anderson's pseudo spin Hamiltonian. The equation THK is nothing but the Anderson's pseudo spin Hamiltonian term in the basis of the two spin or sigma z and the sigma y spin, and the xz and the chi y, chi z and the chi y is nothing but the component of this thing, and I can express my excitation spectrum EK in terms of this. A few basic aspects of the symmetry of this model Hamiltonian is quite appealing, so I can register myself to also the symmetry study. I have also published, one of my paper, Nature Scientific report, the citation as even below. This model Hamiltonian as the time reversal symmetry. Here I only give the result. The detailed calculation here will be found on that citations of this Nature Scientific report. And the other is the charge conjugation symmetry, or in the other words, you can say it in terms of the particle hole symmetries of this model. So this model Hamiltonian obey the time reversal symmetry, charge conjugation symmetry, and the chiral symmetry. This model Hamiltonian is also, it's a product of the time reversal and the charge conjugation. You can express in terms of this. It is also invariant under this, and this is the citation of this detailed calculation. If anyone can interest, you may find it, the detailed calculation on this. And the parity symmetry, we have shown this model Hamiltonian obeys the parity symmetry. CP symmetry, this model Hamiltonian also obeys the CP symmetry. But the most important thing is this, the PT symmetry. This model Hamiltonian does not obey the PT symmetry. Okay, so without introducing any complex potential in the system, we will find for the real potential, the PT symmetry has broken, or in other words, that is this model Hamiltonian system, intrinsically it is symmetry Okay. And the CT symmetry with that is obey the CT symmetry, and the CPT symmetry, it does not also obey the CPT symmetry. Okay, that is the most beautiful aspect of this model Hamiltonian system. I have already told when Professor Sujit Chakraborty has at first introduced this model Hamiltonian in the year 2005, and then he followed the another one more paper in the 2012 ERB. More than 200 physics group across the world have studied this Hamiltonian system, but now the thing is this: none of them has studied the symmetry of this for this model Hamiltonian explicitly. Now, for the Hermitian system, we would like to see the quantum critical lines and the PDJ,
Si on va en reparler, c'est vraiment pas...
Hamiltonian. That is the energy. Hello. I am audible and my internet connection is okay.
That's all fine. Keep going.
Okay. Quantum critical Lagin and Ogoliova Higgins equation. That is this energy dispersion, and also I have written the Kz and the Chi in terms of this theta k in the literature called the topological angle in terms of the Anderson pseudo-spin Hamiltonian. You see how the unit vector making an angle with the reference atom line and how it circulates across the origin. That is the measure of theta k. So the quantum critical line I have expressed in terms of this, which occurs at 3 distinct points on the Galois zone. So I have expressed one is for the k equal to 0, and the other is for the k equal to pi. K equal to 0, the quantum critical line, lambda 2 equal to mu minus lambda 1, and for k equal to plus minus pi, we find the analytical expression for the another critical line, lambda 2 equal to mu plus lambda 1, and for the other case we find the analytical expression of the quantum critical line. This model Hamiltonian, Hermitian part of this model Hamiltonian system is the 3 quantum critical line, and we have obtained got this 3 quantum critical line from the condition mod of ek mu lambda 1 lambda 2 equal to 0. Now I may express my model Hamiltonian in terms of the momentum space as usual when the pupil studied the winding number calculation. But if one wants to calculate also the age mode physics simultaneously, one can also write the EDG Hamiltonian in terms of the lattice spacing, where the submatrices I can write, that is this hopping term, the nearest neighbor, next nearest neighbor, and this is the chemical potential, and that is the delta ij. The delta ij I can express in terms of lambda 1, lambda 2. Equation 5 are the components of the model Hamiltonian in real cases. If we consider the n sides, then this Hamiltonian will be the n by n plus, but it's here the UN eigenvalues. The spectrum of the BDG Hamiltonian will always come in the pairs plus minus, because due to the particle holes symmetry. We have shown it explicitly in one of our published paper, which I cited in the references, Journal of Physical Society of Japan, where the minus side indicates the symmetric nature of the spectrum of EDG Hamiltonian. And this is the topological phase diagram for the Hermitian counterpart of this system. We express, you see here, AD equal to lambda 2 equal to mu plus lambda 1, which corresponds to the k equal to 0 in the momentum space, and the lambda 2, that is the ABC equal to lambda 2 equal to mu minus lambda 1, which corresponds to the k equal to plus minus pi in the momentum space, and the EB equal to lambda 2 equal to minus mu, the third quantum critical line, which corresponds to the k equal to cos inverse minus lambda 1 by 2 lambda 2. Okay, that what is the case? So we can also, this ABC is a very interesting quantum critical line. I would like to give the full credit to my 3 PhD students. They at first find this quantum critical line up to AB. We mark as a CP1 and the BC mark as a CP2. In the CP1, although it's a gapless excitation, quantum critical line, but they have found that is this here, there is no W topological invariant number 0, but the BC W equal to 1, topological invariant number equal to W equal to 1. And also I would like to, very end, I would like to say you the something that is the principle of least topological invariant number. At the end, I would like to explain this, how it is come, and also this started the age mode physics. I would like to give the credit to my all 3 students to find it explicitly, but I would like to, especially that Rahul explored this in his PhD thesis. It may call in the future, it may some people call the Rahul's line for the topological quantum criticality. Okay, I will be very happy on that day. Okay, the topological characterization of the iron ore, I can express my order Hamiltonian system instead of the spinless permanent system to the iron basis. So I can write the spinless operator Cj dagger equal to Aj, Ej2 and Cj. So the just the Hermitian conjugate of it. I can write this Hamiltonian in terms of this operator sum, and then finally we write it in terms of the Fourier space function, complex function. So the one of the references of Rahul is the first author, the Journal of Physical Society of Japan. We have shown explicitly this calculation in the appendix, and so after this is the solution of this complex function, we have got this, which are the zeros of the function fj. The topological invariant W is defined as equal to number of zeros nz of the order of the pole, and np is the inside of the circle. If we do the complex analysis, it can come explicitly detailed, particularly the book of Lebovich on this complex analysis. We have learned it explicitly from that book. So in this case, the winding number equals to the 0 inside zeros inside the unit circle. There is a pole np equal to 0. Zeros inside present the topological phase. On the circle, it present the point of criticality. Outside, it present the non-topological phases. So here I give some example, 2 example of it. Kindly say I take these 2 examples from this published paper of this references, cited references. If you see in the both here case, it present only the quantum critical line lambda 2 equal to mu plus lambda 1, and the lambda 2 equal to minus u, the first and third. The second line we would like to come because the second line has some speciality. So we come in the data. If you see the upper panel and the lower panel, for the both panel, the left curve is corresponding to the lambda 2 equal to u plus lambda 1, and the height curve equal to lambda 2 equal to minus u. If you see in the upper panel, one of the dot inside the unit circle, according to our description, this system is in the topological states. And now the question is this, but in the right circle, if you see the 2 dots only, there is no dots inside the circle. The system is not in the topological state. And similarly, if you come in this case, the other parameters case of the system, okay, lambda 2 equal to minus mu minus lambda 1. Okay, so if you see in this case that here it's a unit circle representation. The upper panel is a unit circular representation, and but the over circle, over panel is for the parametric space representation. Now in this figure, we are comparing whether this unit circular representation for the complex from the complex analysis is correct or not from the parametric space representation. Okay, for the parametric space representation, we are showing this is the case. If you see here, only one of the point touches and the other point is covered by the circle. So here W equal to 1. But if you see in this case, that is these 2 points just touch the origin. Okay, so in this case, the W equal to 0 as we got the 2 points in the upper panel. Now the question is this. Now the special quantum critical sign. Okay, the special quantum critical sign is this lambda 2 equal to mu minus lambda 1. Here in this case, we have also done the same thing. The upper panel is the unit circle representation, and the lower circle is the parametric space representation of this Anderson pseudo-spin Hamiltonian system. But the upper panel, we do the complex analysis standard. We follow the complex analysis book of Lebovich. Okay, so the thing is this: if we see in the upper panel, if you see, it is a W equal to 0 to 1 condition. If you see here W equal to 0 to 1, here the 0, here the just touch 1, here one of the inside dot is inside, W equal to 0 to 1 transition. Also, if you see in this case, here you see here just touch, but here only one of the parametric curve, one of the point encircled by it. Okay, so now the question is this: bulk boundary correspondence. Bulk boundary correspondence is a very holy principle for the topological state of matter. Either the system is in this Hermitian or the non-Hermitian case. Okay, now the question is this. Now I come to this point again. Okay, if you see that is the energy dispersion for the upper panel is equal to lambda 2 equal to u plus lambda 1, and this energy dispersion in the lower panel lambda 2 equal to minus mu. I have already been told you when I introduced the EDJ Hamiltonian in the lattice spacing, the system has a 2n eigenvalue. So we take the lattice side 40 and we are getting the 80 eigenvalues. Okay. Now the question is this: if you see here, in this case, we are getting the zero mode physics. Majorana zero mode physics is occurring at the edge of the sample. If you see here, the finite size length L equal to 40 sides, at the edge L equal to 0 and L equal to 40, we find the finite probability of the Majorana harmonics. Okay. Okay. Now this is the dispersion. This curve is occur at the K. This quantum critical line appear K equal to plus minus pi. So the order of K, if you see in this case, both of the cases K collapses at the K equal to pi, plus minus pi. But in this parameter space, the thing is this: lambda 2 equal to minus u for this parameter space of the quantum critical line. We have not find any zero mode solution. There is no zero mode solution. You see here, we are getting only the oscillatory picture in the system. There is no Majorana zero mode, and also you see in this case the gap closing occur for the finite values of K equal to cos inverse minus lambda 1 by 2 lambda 2, as I have told you. Now that we come to this special quantum critical line. Okay, the special quantum critical we got for the Hermitian case, lambda 1 equal to 2 and the lambda 2 equal to minus 1. This, if you see that the Hermitian case, in the Hermitian, that is the topological quantum phase diagram, it has a 2 quantum critical point. One is the bicritical point, which is appearing on the lambda 1 equal to 0 axis, and the other is the multi-critical point, which appearing as a lambda 2 equal to lambda 1 equal to 2 and the lambda 2 equal to minus 1 case. Okay, now the question is this: if you see the special quantum critical line, when lambda 1 is then 2u, as we have seen, or the system is the non-topological, means there is a winding number on this quantum critical line is equal to 0. If you see here, the winding number, the probability of the 2 edge mode of this is of the order of 10 to the power minus 5. Okay, so it's a small, but if you see when lambda 1 greater than u, that is the OR panel, you see the explicitly that is the 0 mode solution in this case, and a finite probability at the 2 edge mode physics. And if you see the dispersion, this dispersion occur, this quantum critical line lambda 2 equal to mu minus lambda 1 occur for the k equal to 0. So the two curve upper panel and the lower panel of this energy expression is touch as the 0. Now the question is this: so we have got the more explicit. I have already been told you over 200 work from the many eminent physics who across the world has done on this model. At first, this model Hamiltonian appeared in the year 2005 HR physics, almost 18 years, but the none of them are able to find this. Even I have worked before Ahul and my two other students work on this model Hamiltonian system. I will not have able to find these interesting features. This my PhD student has got these 3 interesting features, especially Ahul. Okay. Now the question is this: eigenvalues. If I plot the eigenvalues with respect to lambda, not in the set side, not in the number of eigenvalues. If you see at the lambda 1 is then 2 mu, the system has a gap, and this gap closes at the point lambda 1 equal to 2 mu, and is started to the gap closeness equation eigenvalue. So this point is the multi-critical point, as I told you, lambda 1 equal to 2 mu, and if you put it here, then it comes lambda 2 equal to minus 1. So in this case, lambda 1 greater than 2 mu will find the 0 mode phase. Okay, and also here I have shown you explicitly. Now this thing is this non-Hermitian order Hamiltonian. The main motivation of this work, why this work and the accessories of this work, which my group has done, as highly appreciated by the many physics group across the world. Okay, so the thing is that now how the topological quantum criticality for this non-Hermitian order Hamiltonian changes. Either drastically new physics come or a parallel shift from the Hermitian order Hamiltonian. Now let's see. So to change this Hermitian order Hamiltonian, I can go to this by adding this I gamma term, complex term in the chemical potential. Then I do the Fourier transform. After doing the Fourier transform, I can hide my Hamiltonian, hide the Hermitian one. It's called this Anderson pseudo-spin Hamiltonian for the non-Hermitian order Hamiltonian system. Okay, complex potential energy or chemical potential. I can hide in terms of this. Also, one can find the winding number is this, but here we have not found this process. We have found the 0 mode solution. We will come to this point in detail. The phase diagram of this order Hamiltonian coming, I can express this equation Hamiltonian H in terms of the schematic representation in terms of this. Each side, the new plus I gamma, I can the AI EIJ to my Harman for the each side, and the lambda one is the nearest ever hopping. Also, I can express in terms of the.
Can I ask you a question? When you add this I gamma term,
lambda 2 is the nearest ever.
Can I ask a question? When you add this, when you add this I gamma term, is the Hamiltonian just complex, or is it PT symmetric?
No. PT
No, what?
Okay, sir, if you see the calculation in detail, then you will see that is whether I add this I gamma term, this ordinal Hamiltonian itself, the Hermitian part of this ordinal Hamiltonian, when the I gamma term is absent, it itself is the not, it is symmetric. For that reason, I have shown the all symmetry properties of this ordinal Hamiltonian system. This ordinal Hamiltonian system has very beautiful and interesting symmetry properties. And my all calculation I have done on that paper, detailed calculation. It's the mathematical output of it, sir. Okay. Now, okay, kindly ask me, sir.
So can you identify the PT symmetry? In the chat, there are several comments. People say that it's not PT symmetric.
No, it's not intrinsically. It is not. It is symmetric when the I gamma term is absent.
Okay.
That is one of the beautiful aspects of this ordinal Hamiltonian system.
If it's absent, but if it's present, then it's PT symmetric.
Present means no, sir.
This is not PT symmetric.
No, it is symmetric.
Okay.
Now the thing is this, kindly see this phase diagram. Also, I will come to the other phase diagram after 4-5 slides. Okay. If you see after, and the thing is if you see for the gamma 2 equal to positive, just this the lambda 2 means the imaginary part, non-Hermitian is nothing but a parallel shift. Okay, but when the lambda 2 became the negative, okay, when you see the system as a parabolic term, and I would like to come to this point. If you see here, the point P is the multi-critical point at the point for the Hermitian is equal to lambda 1 equal to 2 and lambda 1 equal to -1 is shifted to the equal to lambda 1 equal to 0 and the lambda 2 equal to some square root of this value. So almost is some sort of the bicritical point. If you see that Q is the bicritical point. So the multi-critical point now to transfer some sort of the bicritical point, or the multi-critical point, I can say W equal to 0, W equal to W to 1. I would like to come to this point in detail. Now, this Hamiltonian, that is this phase diagram, topological quantum phase diagram, we have done in terms of the detail of the zero mode and analysis of the topological characterization. Okay, this is the value explicit we have done, and this is the line W equal to 1. Zero mode solution, line 1 is the I guide line. I guideline is this, is the x plus minus 1 less than 1 system is in the topological state, and if x plus minus 1, as we see the E1 in E2 dot, system is the gapless transition state, and when x plus minus greater than 1, as we see so present, then there is no topological state. Based on this zero mode solution, Rahul has constructed this topological quantum phase diagram. The same thing I can express in terms of the unit circle representation. means this line W equal this line 1 now became a circle of this unit radius. If we go to the parameter space and we can find the here W equal to 0 to W equal to 1 transition in the upper panel, and the lower panel, if we will see here the system as a W equal to 1, W equal to 2 to W equal to 1 transition, or the vice versa. W equal to 2 red dots, and here is the 1, and here is the transition point. Here is the transition point going. The lower panel equal to W equal to 2 to 1 or 1 to 2 transition. Okay. Now the excitation spectrum of the topological quantum transition. I have already been shown you what is the Hermitian counterparty, but the non-Hermitian counterpart is very much interesting on it. If you see here in this case, okay, the thing is this, that is the upper panel and the lower panel, that is the energy spectrum mod of is plotted with respect to the K, means the momentum space for the parameter space of the bicritical and also for the multi-critical points. And we can see for the lambda 2, for the lambda 1 equal to 0 and the multi-critical point lambda 2 equal to square root of 2.0, as I told you earlier. Okay. Now the question is this, lambda 2 equal to 0, as I told you earlier. Okay. Now the thing is this, that is this lower panel. If the lower panel is this, we have plotted the eigenvalue with respect to the lambda 1. We have already been shown you for this Hermitian counterpart. If you see, that is this Hermitian counterpart here. Here the EL and red and blue card represent the EL and imaginary part of the zero mode eigenvalues respectively. And the inset, if I do in this case, inset is the Hermitian one, gamma equal to 0. Now I would like to explain why it yet physically. Yeah, that is this physical explanation of it. A part of the physical explanation which I have written in the second column, I have already been explained in the book. Now the physics of this other column is this. In this excitation spectrum along the red critical ions, okay, the behavior of the zero mode eigenvalue in the open boundary setting in the Hermitian gap closing point 0, 0, 0 respectively. This gap closing point do not change along the respective critical lines for the Hermitian case. But in the non-Hermitian case, due to the presence of the gamma term, okay, non-Hermitian term, it is observed that the gap closing point continuously changes along the critical line points and corresponding to the change respectively. These gap closing points do not changes along the respective critical lines. In non-Hermitian case, it is observed that gap closing point changes continuously along the critical line. So we have solved this equation explicitly in terms of this. And we have got the K plus minus value, eta 1 and eta 2 for the different setting. We find these 4 combinations. And the combination is this, bicritical point are these K minus plus K plus, okay, different setting in the excitation spectrum. Similarly, at the multi-critical points, all 4 equations of the K provided the location of the gap closing in the excitation spectrum, and the excitation spectrum, the K equation along the blue critical lines. Okay, so now the question is this: that real and imaginary component of the spectrum, in mathematical analysis of it. Okay, so if we do this equation, I will get, and if you see the Chi-Z term is only modified by the I gamma term. So I may do this complex analysis in terms of this. If I do the complex analysis, we got the R term equal to this and theta term equal to this. And equation 20, the real part I can write in terms of this equation, and the imaginary part I can write in terms of this equation, two part, okay? The two gamma, if you see here explicitly. So if we plot this, the theta, there is this complex analysis topological angle, and the real part H2 and H1, we show this behavior. This is the part we are going to submit in the archive very soon. Ilanion is the collaborator of this part. He's contributing, raising the very question at the fundamental level and the intelligent level, and Rahul is taking almost the leading role of this two complex analysis and the physical explanation of this. Okay. Equation figure 7, theta and gamma induce the argument which is a significant effect on the behavior of the real and imaginary component. In this section, we discuss theta on the real imaginary component, compromise the left and right angles, as I show you in detail. Okay. So H2 and H1 and theta, K in the right panel plot, H2 is positive, then H1 is negative, when H2 is also, H1 is negative for the different case, and we'll find this symmetry from this principle. That is a theta equal to pi, and also the theta equal to minus pi, depending for the K equal to 0 and the others. Okay, F10. And if we see the C and D of the figure 20 of the right panel, when you see instead of A and B, theta plus pi symmetry is goes to the theta minus pi symmetry. So investigating in detail, okay, investigating in detail 20 in detail with the help of theta, we come across the cosine and sine terms for real and imaginary component respectively. When theta is negative, the real and component consist of the term dependent function. So hence the real component of the eigenvalue ever from positive to the negative quadrant like the imaginary component. So this is the basic root, basic source of the origin of the real and imaginary eigenvalues, which we have shown by the blue and red color in the previous figure. Now I would like to come to this exceptional point. You know the all of them exceptional point is a really exceptional point for the non-Hermitian system. And also we know this exceptional point is a dramatic effect on the system leading to the non-trivial physics with interesting and sometimes counterintuitive features. The QT symmetry breaking occurs when fluorescence of the eigenvalue state and that of the corresponding eigenvalue at an exceptional point in the discrete spectrum. And those are the all application of the physical system of the exceptional points. Although it has appeared as a mathematical curiosity of the non-Hermitian system, but the mother nature blessed those mathematician or the originator to find in the other nature explicitly. And also the parametric curves and the exceptional point is very simple. You can find these references in the any references source. So we would have also taken this very simple 2x2 matrix, and at the eigenvalue j greater than gamma, pt unbroken, EL eigenvalues, but the j is then gamma is the pt token. So for our case, it's an imaginary term, HZK and HI gamma complex. I can write it in terms of this. So for the E equal to 0, when the exceptional point will be occurred, the condition is this HZ equal to 0 and HY equal to plus minus gamma. This condition HY plus minus gamma give the location of the exceptional point. Now we will find this is this transition in terms of the exceptional point. For the Hermitian case, we have done the unit circle. Also here we will come. And for the non-Hermitian case, we can find the parametric space in the chi-y chi-z in terms of the exceptional points. Here, these red dots are the exceptional point. If you see in the upper panel, that is this from the 0, none of the exceptional point enclosed by the parametric curves, but here two exceptional points just touch on the surface on the line of the parametric curve. It is the transition point, and in this case, this exceptional point are inside this parametric curve. That is the system is in the topological state. Okay. Now the thing is this. In that case, also we'll find here that is the initially the system here W equal to 0 to W equal to 1 transition in the upper panel, and in the lower panel W equal to 1, the two parametric space point close W equal to 1 to W equal to 0 transition. So the parametric negative lambda value I can also do for the other region here. In this case, W equal to 0 to W equal to 1 transition in the upper panel, and in this case that W equal to 0 to W equal to W equal to 1, this transition I say, and similarly the parametric space plot for the W equal to 1 to W equal to 2 transition, W equal to 1 to W equal to 2 transition, 2 parametric space point has done. Here the 2 and in this case, no, here the, yes, here the 1, 2, and in this case, here also the 1 and here also the 2. That is the 2 winding of this card. So the bulkage properties at the quantum criticality for the non-Hermitian case. For in this case, you will find the Majorana ports for the OR values of gamma to the higher value, OR values for the negative lambda 2, for the positive lambda 2, it is nothing but the parallel shift, but for the negative lambda 2, we will find it's not the parallel shift. For the OR values of this gamma, the system is almost touch. You see the, but for the higher values of the gamma, that is the line of separation between this topological quantum critical line is variable line. How much? As you increase the number of at its side, the eigenvalue tends to 0. The 0 mode solution is more available for you see 10 to the power minus 17 and up to the 40 sides we are getting 10 to the power minus 13. So the eigenvalues is more or less is a good thing. And now the generalized phase diagram for the non-Hermitian system. For the non-Hermitian system, the generalized phase diagram for the positive lambda 2 to minus negative lambda 2, also the positive lambda 1 to minus negative lambda 1 explicitly with present. This is also from the 0 mode solution of this paper. Now the question is this: the effect of the non-Hermitianity on the topological phases and criticality movement of the critical lines. We have shown the critical lines. Now the critical lines, how they move, we show it explicitly in this case. Here we presented the lambda 1 versus gamma. Lambda 1 means the x-axis or the abscissa. Okay. Now we take the 3 different values of lambda 2 as depicted in the figure. Lambda 2 equal to 0.4, lambda 2 equal to 2.2, and the lambda 2 equal to minus 0.9. These different values of lambda 2 is give me the different type of transition, winding number transition in the parameter space. Okay, it differs from the study the transition of the negative lambda 2. If you see the lambda 2 equal to 0.4, it go increasing as you increasing the gamma, the movement of the critical line. And for the lambda 2 equal to 2.2, it is going down in the critical line. If you see my non-Hermitian topological quantum critical line, you will find it more explicitly in this case. But if you see here, if we take the lambda 2 equal to minus 0.9, that is the negative quadrant of the lambda 2, we will see initially it decreases and it's going to increases. That is the instead of studying the lambda 1 versus gamma, instead if we study the lambda 2 negative quadrant of the lambda 2 as a function of gamma, because the negative quadrant is the more, okay, interesting. It is changing the topological quantum critical line completely in a different way. We will find it is decreasing along this line. So here we would like to express in terms of detail the movement and the direction of the chemical potential, the direction of the critical lines, the same kind of theta space which I have just explained you, and see if lambda equal to 0.5, it is increasing, and this increment is the gamma xn plus 1 minus xn is saturated, and also in this case lambda 2 equal to -2.2, as we show it is going down. You kind of see is going down to the other space, okay, and this increment is itself in the same quadrant. You see the ordinate are also all negative, but in this case the ordinate changing from the negative to positive. So we put the 0 line as the mark line of demarcation. Also here put the 0 line, the line of demarcation. Okay, now the conclusions of the work. We have presented the Hermitian topological quantum criticality and the critical lines and multi-critical points. We have presented the results of the zero mode physics of Hermitian system. We have presented the results of the non-Hermitian topological quantum criticality, critical lines and multi-critical points. We use the parametric curve and also the exceptional point solution. We have presented the result of the zero mode physics of non-Hermitian physics, also for Hermitian physics. We have also started the movement and the direction of the quantum critical line. We hope that this work will give a new perspective. This work will give a new perspective in this quantum criticality in the non-Hermitian quantum system. My humble request to the authority of PH, the Journal of Physics conference series, then maybe this series will be more interesting across the world. Okay. Now the question is this. Thank you for your kind attention. Comments and suggestions are welcome. My email ID is this. Okay. And I am ready to get any questions and comments.
Thank you very much. Questions, comments? We don't have any questions or comments. I have a small comment. At the beginning, you said that at the beginning you had some number that there are more than 2,000 papers written. I think you need to update this. Well, the Bender-Bircher paper has almost 6,000 citations. So judging by that the number is a lot higher.
Okay, so then maybe it's 10,000 or 20,000.
It's not that important. It's just a minor comment.
Okay. Okay, sir, I will search it. Eh?
Any other comment, question? Then let's thank Sujit again. And we see again in 2 weeks.
Okay, sir.
Bye, everybody. Thanks for coming.
Thank you very much.